theory of structures, and the key here is the matrix method. And you've seen your syllabus is also asking us to talk about this, the force method. The force method was originally developed by James Clerk Maxwell. This is a Scottish mathematician and physicist. Scottish physicist and mathematician in 1864, and later refined by Otto Mohr and Heinrich Müller. These are German civil engineers, and so that's for the first method. They are related with the displacement method, as you will see. So the force method consists of writing equations that satisfy compatibility and force displacement requirements for the structure in order to determine redundant forces. Once these factors have been determined, the remaining reactive forces on the structure are determined by satisfying equilibrium. What we are trying to say here is so you have a structure here. First, we are talking about statically indeterminate structures. If you remember, statically indeterminate structures are structures first statically determinate. So statically determinate means that you can use the three equations to solve them. You can use the three equations to solve them. So the three equations are summation of forces in the x direction is 0 or horizontal direction. Summation of forces in the y direction is 0, and summation of moments at a point, say A, should be 0. So for statically determinate structures, which you should have done in second year, can solve these equations together. But for in third year, you now start talking about statically indeterminate structure. That means that in addition to these equations, you need other equations to be able to solve. Those other equations comes from compatibility. For example, compatibility in terms of geometry, compatibility in terms of displacement, compatibility in terms of deformations. So just to explain a little bit, what I'm trying to say is, this is statically, if we have maybe say this is 50 kilonewton, and this is so this is 3 meters, and this is 3 meters. So this is statically indeterminate structure. Statically indeterminate means the number of reactions are more than the equations that can solve them. So for example, here the reactions would be RA, the reaction at A. There is a horizontal force at A. No. So let's call this VA for easy reference, VA. So there would be horizontal force there, HA, and there would be a moment there. I don't know the direction, let's assume. Maybe not. There will be a moment there, MA. So those are three reactions. And because you've added here, these are four reactions, RB. Of course, because this is a roller, HB is known to be 0. This is from basic understanding. So therefore here we have four reactions, but only three equations. The three equations we are talking about are these ones. The reactions is this, that, and the moment, and RB. HB is already known, so you cannot count it. We know it's zero because by definition, the for a roller support, the for roller support, the horizontal force or horizontal force is zero. So to solve this, you will need to uh, to reduce this to a structure to statically determinate, which you can solve. So uh, you will remove the support at B. The easiest, also probably there's another way to do it, but you find the easiest way to do it. If you remove the support at B, then you're able to solve with 50 there. Then you can solve the reactions and then replace. So, and then also replace with the support there with a reaction at point B. And this this equals this plus that. So this is statically determinate. This is statically determinate. You can solve each at a time. Now, of course, knowing that at this point, uh, because there is no support, there will be a displacement of delta B, let's say. And so that displacement delta B, so the compatibility equation or the compatibility situation, if there is a support there, there cannot be any net displacement. Of course, unless the net displacement is prescribed, but we will say in our equation, in our final equation, that uh, therefore, uh, assume the displacement here would be RBB times, we'll talk about this in detail, FBB. So therefore, to solve the reaction at B, because we know this displacement delta B plus RBB times FBB either must be zero, or if there is a prescribed displacement. So because by definition support cannot have any displacement, has to be zero. So using this, you will be able to solve this. You will be able to solve this. The only thing you won't know is the reaction, which from the equation you should be able to solve. So because I need you to understand, if there is a question unknowns in the so the equations are these equations are displacements. Once the displacements are obtained, the forces and the and are determined from the compatibility and force displacement equation. Like I've already said, at the support, you find the forces and also the displacements, and the compatibility is condition is that at the support there can be not be any there is no net displacement, of course, unless the question specifically tells you that the net displacement is this, then you can equate. But what we expect is there is no displacement. So based on compatibility, then we're able to solve the problem. So in the force method, what are unknowns unknowns are the forces. The equations used for solution are compatibility and force displacement equation, and we use the flexibility coefficient. What I have used in the previous case actually is called a flexibility coefficient. And this is why I was saying that it's quite difficult to get these things, to separate these two methods. This is what is called flexibility coefficient. We will talk about it in detail, and then the displacement. So they are quite close to each other. So unknowns are displacement in the displacement method. The equations to be used are equilibrium and force displacement, and then the stiffness coefficients. Now the stiffness coefficients and flexibility coefficients are more or less the same thing, because if the same thing that is flexible can be stiff, so it's the opposite of each other. So in that realm, we are more or less talking about the same thing. So the force method, so basically how to use the force method of analysis, the general procedure. From a free body diagram, there would be four unknowns, like I've said. Four unknowns, remember I already said here, this is VA, this is HA, and this is MA. Because by very definition, this is a fixed end. Fixed end can give us all the reactions already shown. So 3 here, and this is a pin. This is a pin. So pin can give us RB, but pin can also give us HB. But this HB has to be 0, because uh, there's no horizontally externally applied load. So this has to be 0. Of course, by definition, so this cannot be included here. Now this HA, because someone might say, then if we know HB is 0, then HA of necessity has to be 0. But there could be, if for example the okay, there are instances where the HA cannot be a 0 of necessity, but HB here is known to be 0 by intuition, and actually by the very nature or by the very definition of the kind of arrangement that we have. But here, because of by the support, we already know that the fixed support can give the reaction in both x, y, and also a moment. So we have to include it. So here there are four unknowns, and then 3 equilibrium equations, and then we can say the structure or the beam is indeterminate to the first degree. So if it's indeterminate to the first degree, then now the degree of indeterminacy determines how many additional equations are required to be able to solve the problem, in addition to the 3 equations of equilibrium. So because this is just 1 degree indeterminate, you need one more equation, which we derived from displacement compatibility. So use the principle of superposition and consider the compatibility of displacement at one of the supports. The same thing that I've done, because just to make sure you understand, I will have to keep writing the okay, let me repeat, assume that I did not say. So you remove the support at point B, and you still have your support, and with this load, of course, this is uh, gonna be displaced like that, and let's call this displacement delta B. All right, so this is all we are saying here. And then, so this is the first part. In the second part, you because this is now statically determinate. Actually, you can use the 3 equations to solve as well. Again, this is also determinate, structurally determinate. RBB, RB, okay. And of course, this one will also try to deform in some way. Let me try my best. may also deform that way because you're pushing it up, and the movement there will be RBB. Will actually there's something to understand there. This displacement would be based on the flexibility of that support. So that would be RBB times the flexibility. Assume the flexibility of that support is FBB. All right. So if you add these two, you should get your original beam. But we know at that support there cannot be any net movement. So 0 plus delta B plus FBB times RB should be 0. This is known. This will be known. The only thing you don't know is RB, and then you're able to solve your problem. So this is what we are trying to explain in that. Okay, I have already explained it shortly, so maybe we just read because this I didn't know that this is where we were heading. So you choose one of the support, so RB, and I would say you do it intelligently because you can choose any other. Probably you're able to solve, but with more effort, much more effort. So whatever you choose, please make sure it makes it easy to solve, not make it difficult to solve. So, like I've said, if you remove uh, the support at point B, the displacement would be delta B. And here, so we remove the rocker or the pin at point B. As a result, the load P will cause B to displace downwards, as already shown there. And then by superposition, the unknown reaction at B causes the beam to go upward, okay? And then when you add the two, there cannot be any net displacement because by definition, the support cannot move. So you add the two to give you 0, except also you can be told that the net effect is that the support displaces by 5 millimeters. If that is what you are told, then you have to put 5 millimeters there. But in this case, there's nothing, so you equate the two. This now this is on the based on the principle, but then how do you evaluate these specific values that we talk about? There's the A delta B. Of course, I expect you now to know, for example, if you have these have standard formula, which I expect you to know. For example, if you have a load there, P, there is a standard value of, there is a standard way to get that displacement. Actually, you can do it as at first principles, but there is also a standard. For example, I believe you should know that if the load were here, then that displacement would be PL cubed over 3I. You should know that. This even if it's not at the edge, and you as long as you know this distance A and distance B, you should be able to get the displacement. This is what we are talking about. So from there you know that value, and so the first letter in this double subscript notation refers to the point B where the deflection is specified. The second letter refers to the point B where there are non-reaction. Okay, this is just some notation to make this easy to grasp. And then let us denote the displacement at B caused by a unit load acting in the direction By. Yes, so By. So to help us, because we need this, we already know. from the standard formula. I'll show you how to, in case you don't know. So you can get this displacement from standard formula, or you can get from first principle, because this is a statically determinate beam. Now this, if you remove, if you add now the RB, the reaction itself, then you get what is called delta BB. Then now let's delve a little bit in detail how to evaluate this value of delta BB, and that's where we are going to introduce the flexibility coefficient. So let us denote the displacement at B. So assume point B, and we use this a lot, the virtual work, the principle of virtual work. Assume there's a unit load acting in the direction of By as the linear flexibility coefficient FBB. So FBB is as if there was a unit load. And why do we want to do that? Because if uh, a unit load sorry, no. So if this is 1, and can move this point FBB, one can move that FBB, but so RB, if RB of this, so how about if we have RB? All right. So RB would move, this is what we are defining as delta BB. If one can move it FBB, if one can move FBB, how many times can RB move? What is the value that RB can move? Anyone? Here. So in my case, I was using this as RB, but in the notes it's BY. So I think it's just the same thing. It's the same thing. So BY times FBB. And so in specific terms, so the linear flexibility coefficient FBB is a measure of deflection per unit force, and so it's units are meters per Newton, and the compatibility equation above can be written as shown. All right, and so using the method of virtual work, the appropriate load displacement relationship for deflection delta B and the flexibility coefficient can be obtained, and the solution for By be obtained. I had said that you can sorry, in my explanation I did not take care of the direction, but please note that if you remove the this, and depending on what you assume is your direction, so assume this is negative, so you can see that's why you can see, assume going down is negative and going up is positive. So please note the direction is also important. I apologize for that. So the like I had said, you already know this, if this was here and this could displace PL, if this is PL cubed over 3EI, that would be the displacement. But now that this is not using the same, I'm just saying they are standard. You can, it depends on you. There are standard ways you can even solve from first principles. So if this is here, the displacement can be solved. Uh, this work is offering us a very easy way. Normally, the principle of virtual work is a good, excuse me, can always help us to solve the problem. So if you know the result from first principles, or you can use virtual work, or you can use indeed any other method. You can use conjugate beam as well to get the displacement, or indeed any other method. Then you solve delta B, and if you get FBB, of course, uh, virtual work will help us get FBB and delta B very easily, as I will show you. So once this is accomplished, the three reactions at the wall can be found from the equation of equilibrium. The choice of redundant is arbitrary. That means it's temporary. The redundancy is the whatever you remove. The choice of what to remove is redundant. This is what you are saying. This choice is redundant. Indeed, even if you keep this and remove one here, probably you are able to solve, but it will take much more effort. So this is why I'm telling you, you need to think carefully of how or what to remove, and if the structure remains statically determinate, that it can be easily be solved. Now the moment A can be determined directly by removing. So this is what I was trying to tell you. You could choose to remove the B, or remove the hinge. Like you can see here now, the hinge is removed. If you do that, then you are able to directly get the moment at point A. So the moment A can be determined directly by removing the capacity of the beam to support moment at A, replacing the fixed support by a pin support. The rotation at A caused by P is theta A. The rotation at A caused by redundant MA is theta AA. And of course, you know that uh, the the so the moment times this displacement is the moment times alpha AA. Alpha AA is the flexibility coefficient. In terms of moment now, we've said that FBB is, let's go back here a little bit. The RB, we removed RB and replace it by a unit load. But here we have assumed the moment and replaced it by a unit moment. Please note. So, and that unit moment is what we call alpha AA. So, alpha AA is the FBB equivalent. So when we talk about moment, a unit load, we talk about flexibility coefficient, but we can also talk about flexibility coefficient when it comes to moment. So that's what we are saying. And the same idea, just like I told you that you can choose a redundant B. Now here we are choosing the moment as the redundant. If we denote the angular flexibility moment, so it's called angular flexibility moment alpha AA, as the angular displacement at A caused by a unit couple. So you apply a unit couple, a unit moment, and then so theta, the displacement, the rotation would be the moment, of course, times the flexibility. This is the same idea, like if one are you just one going up will cause, if one will cause FBB, the same idea here now. So if you remove the and now talk about it in terms of moment here. then apply a unit moment, just a unit moment there, then it will cause a displacement of delta, sorry, a unit sorry, a unit, or someone said they are not seeing green, sorry. So someone said they are not using green. They're not seeing green. Okay. So if you apply a unit moment here, the rotation there would be alpha AA, the same idea, such that the rotation by everything would be the moment times the effect of 1, which is alpha AA, the same idea actually. So thus the angular flexibility coefficient measures angular displacement per unit couple moment, and therefore it has a unit of radius per Newton. And the compatibility equation of the rotation would be, because again, because we know that in fact, in reality, for a fixed end is not allowed to deflect. So even though we choose a redundancy there and say that it will deflect, and that becomes theta A. In fact, theta A plus MA alpha AA should be 0, because in fact we know that at fixed end there is no deflect. I mean, the gradient cannot be any value but 0. So based on compatibility, then you're able to get the moment directly. So this is another way. I'm just trying to explain another way. Otherwise, even here, once you solve the RB, even here, once you solve this, then you can use equilibrium to solve these other values, including the moment. So I'm just, and this, that's why I was telling you, you have to find a clever choice of the redundancy. Some of you can see, you can also use the moment. But if you're good, maybe you're able to you'll get to the answer. But if you chose the RB, it's much simpler. And even once you figure out what RB is, of course, you will get what MA is as well. So these what Maxwell is telling us as to stop me to understand. So Maxwell reciprocal theorem states that the displacement at a point B on a structure due to a unit load acting at point A is equal to the displacement of A when the load is acting at point B. So it it seems like wordplay, but it's true and also useful. So let's take two identical beams here. So this is point A and B. So you put a unit load here. So the displacement due to this load at point B would be FBA. All right. So that's the first situation. The second situation, here the same beam A, B, but the load now is point B. So the and this, remember, is a unit load, virtual unit load. So the displacement of this at point B is FBA. And how about the displacement of this? The displacement due to this load at point A is called FAB. So Maxwell says that this is the same. The work, the displacement due to a unit load at point A is the same as, so displacement at point B due to a unit load at A is the same as a displacement at point A due to a unit load at B. So that is the Maxwell reciprocal theorem. The theorem also applies for rotations as well. So the rotation at point B on a structure due to a unit couple moment acting at point A is equal to the rotation of point A when unit couple is acting at point B. So that's the same idea. So there's a question. I need to stop here because from here we are going. Yeah, someone is confirming. I need someone to tell me how we can proceed with this solution. The aim is to get the displacement at point B. Of course, in the spirit of a complete so once we choose the redundant, and then we say this is our RB. I like to call it RB, and this is your displacement due to delta BB. How might we proceed to solve this part? Yeah, people are not talking. Class rep. You remember conjugate beam? For me, this is the easiest to solve this part. I might make other choices when it comes to this. So conjugate beam, if you remember conjugate beam, the free end becomes the fixed end becomes free, and the free end becomes fixed. So using the conjugate beam, then we use the let me make it easy for me. So if you use the conjugate beam and draw the bending moment diagram, hello. So if this is the bending moment diagram, this would be 50 times 6, so that would be 300 but just a minute. Yes, so for the conjugate beam, if you remember your so we draw the bending moment but divide by EI. So in this particular case, this is easier to solve. Now for the conjugate beam, so this is A. If you forgot, you need to remind yourself. And B. For the how to get displacement using the conjugate beam is that the moment is the displacement. The moment becomes the displacement. The moment of M over EID diagram becomes the displacement. So you get the moment at point B because you want the display. Getting you, please. Yes. Yes. Hello. We are now getting you. Yeah. So on the conjugate beam, the fixed end becomes the free end, and then the free end becomes the fixed end. Then you draw the moment, but the moment you divide by EI. Now, the moment of the M over EI diagrams becomes the displacement, if you remember I think should have been covered in the previous course. So therefore, displacement at point B is the moment of the M over EI diagram. And how do we get that? So delta B, to get the moment, you first get the area. So the area is a half times 6. The length is 6. The width is 300. 300 over EI. Okay. 300 over EI. Now times the distance between between the center. So the center of this would be, you should know here, this load would be acting. This is a rectangle. Not rectangle. This is a triangle. So this would be 2 meters. This would be 4. So that would be the centroid. Okay, writing here is a little challenging. That would be 4. So times the centroid times 2 over 3 times 6, which is 4 already, plus 6, because we find the moment at point B. So which this is the same as the moment of the M over EI diagram at point B. So plus 6. Now, because I've made it easy for you, please someone calculate how do you get the delta B. 2 over 3 times 6 is 4, plus 6 is 10. I mean, very easy. Please, someone. Hello? Hello? You have no calculators or what? Yes? It seems I am in this class alone. Class rep, I'm here to make sure you understand. So I'm going a little bit. Oh, yes. Okay, good. But you speak because, yeah, that's true. Many people have calculated this. Yes, it's 9,000 over EI, so that's good. So when you see you are not, that's I hope that's the correct thing. So here, yeah, so you can see that's your solution. So let's go back. Let's go back. So here, so we got 9,000. You've seen how easy that should be. Actually, if you knew the standard way to get that, there's a standard table that can solve that easily. But just to demonstrate to you how to do that. So now we've dealt with this. We've dealt with this part that So that's 50. So that is already solved. So we need this. Now you careful here. Again, to use the a virtual work principle. So if you have that, so if you want to apply a virtual work principle, would be the, so to get the displacement, let's okay, I should be I should be asking you, but I remind you. So to get that, using the virtual work principle, would be to impose the integral of m, small m, where this is from the virtual work, over the moment over EI diagram times dx. So I told you need to think carefully. So here, to get this displacement using the moment conjugate beam, was easier. Actually, we could even use virtual work, but it was easier to use conjugate beam. Virtual work, of course, should also give you the same method. So whatever way you use to solve this displacement is fine. There's a standard formula one you can use. If you forgot the standard formula, there's the virtual work, there's the conjugate beam we've done. Whichever method you use, as long as correct, should get delta B. Then now, again, I could use virtual work, but in this case, it's no, I could use conjugate beam. Sorry, sorry, I could use conjugate beam, but a virtual work actually seems easier in this case. So I'll prefer that. So that's your work actually to see. So if you because the principle says what, says that you have to assume a virtual work. So the axis would be like that, and if you assume that you put one unit there, then you'd have a load going, and that would be x, right? Then, so this is the m when you assume, so when you're talking about a unit, again, because the RB itself, the RB itself, RB itself is just in that direction. So again, whatever value you add here would be but the beauty here now, actually m equals m. So again, we'd say that FBB would be x squared integrated over EI dx, but from 0 to 12, which is x cubed over 3EI from 0 to 12. Please note that this is the same thing as, I mean, it's so easy that if you were to load this like that, of course, that's just going up, but we already know this result that, so if this is L, the displacement at this end, we already know as PL over cubed, 3EI cubed. Isn't it the same thing here? It's the same thing here, except now here P is 1. So PL cubed, but P is 1, so x cubed over EI. So 0 to 12, because This is 0, and then you are integrating up to 12. Someone, please solve the problem for us. How many? You so anyone else who is saying the contrary, that this is difficult, is not saying the truth. It should be very easy, if you ask me. So uh, so you can actually use any method that you wish to be able to solve this problem. So having known that, uh, uh, so you know that this is 15.6, and this is 50. And so how much is this VA, please, someone? Speak. So 34.4, and by the virtue, you can get MA. Someone get me what MA is. Let's see the direction of MA. I believe this way. I could be wrong, I'm not sure. This is 15 minus 15 times 12. Which one is more? 15 times 12 minus 15.6 times 12 minus 50 times 6. Which one is more? 15 times 10 is 150. Yeah, so so I think the moment is going up there. How many it is? MA is how much? See which one of you is correct. Is okay, 112. Yeah, the one who is saying 260 something, please check your calculation. So that's 112. So then you draw your. So okay, I remind you, because apparently some students seem to still have problems. So you draw how to draw the shear force diagram. So you come here, you draw 34.4 there. Then once you draw 34.4, you come here, then 50 takes it back to 15.6. Also note which direction. So if up is positive, and then 15.6, and then gets. So because of equilibrium at this end, there have to be 0. Okay, that's how to draw the shear force diagram. To draw the bending moment diagram, of course, you need to know that linear portions will be circular. Excuse me. Linear portions will be I say curve. Will have a curve. So again, you draw here. The sign conventions might change. So here, because there is already a moment there, 112, so you draw. No. This the okay. The sign convention actually doesn't matter. I'm just changing my cosine convention, because you can draw 112 here, 112, but the shear force and the bending moment diagram are always in the reverse, so that's why I'm hesitating. So this is going up, usually is plotted down. The shear force diagram and the bending moment are in the reverse. So this is already 112 there. Now minus the area of and because this is linear, this is going to be curved. So the value somewhere there would be 112 minus 34.4 times 6. Someone please. I don't know. I think it's going to go above the, so it's going to come something like this. And this value here now, and a point of zero shear force is a point of maximum actually the let me going to be something like this. No, it's not very nice. I'm not sure. No. Something like the maximum is going to be here because points of zero should be the maximum. So this value here would be 112 minus 34.4 times 6. And this value here, okay, someone please calculate so we use real values. And then from here is 0 minus 15.6 times 6, of course, will take you back to 0. So that's your shear force diagram. And you can also calculate this point. This point is important. The point where the moment is 0 is important. And you calculate it by saying that this actually, for this to go back to 0, that means at this point, so those who understand, because actually this is something you should have learned in the previous classes. So to calculate this point here, you can say 34.4 times x equals 112, and you get this value there. Anyway, the course, the purpose of this course is to make sure you end here. You can calculate the moment, the reactions, and so on and so forth. Now, the rest of this, how to draw shear force diagram, is assumed you should have learned, but now I'm trying to remind you, and I hope it's clear. Let me record. In our case, we were, this is what we were doing, and then the x, and then we are saying m over ei. So we are integrating this because we said m equals m. So the same. So you can see this. Yeah, is this. We're integrating this. And which one now? No. We're integrating a triangle by a triangle. So a third m times m prime times L. And remember, in our case, actually, it was x. One was x times x, and the length is also x, all right, over 3 from 0 to 12. So anyway, if you do this, I think this is some way, some standard way. If you're integrating two known shapes, then you can easily know the result. So in our case, this is what we use. You can see we used x cubed over 3. That's yeah. So this is one way, or you can integrate the way we did, whichever works for you, whichever one you find easy to understand. So just to recap, if the bending moment, if the shear force diagram is linear or is constant, sorry, the bending moment diagram is linear. And if the shear force diagram is constant, then the bending moment diagram is linear. If the shear force diagram is linear, the bending moment diagram is a curve. And if that means you this goes to the principle of dm. If you differentiate dm dx, if you differentiate the moment with x, you get the shear force diagram. That's why we have that kind of relationship. Yeah, anyway, and like I was saying, for the purpose of this course, that you're able to evaluate these reactions, to draw the moment diagram, I think that you already have done in the previous courses. And of course, just for the clarity, if you differentiate the shear force diagram with respect to x, then you get the load. Okay, so and that means if you integrate the load, integrate the load, integrate the load, you get the shear force diagram. Integrate the shear force diagram, you get the moment diagram. That's why if you differentiate the moment diagram, you get the shear force diagram. That reverse relationship. Okay. If there's a question, I'll pause here so you can ask.